Welcome to session 3 of Unit 3, and in this session we'll be looking at the integrated rate law. By the end of the session, you should be able to derive the integrated law for first, zero, and second order, plot a curve and deduce the order of a given data, derive the half-life of first, second, and zero order reaction. Now, first order. For a first order reaction, we earlier on noted that or studied that rate is equal to K concentration of A. So, to find the integrated, we first of all take the natural log of A, and since K is a constant, we all know the integration of a constant, what it means, times time plus the natural log of the initial concentration. So note that this is at time t and this is at time or the initial concentration. This is the final concentration of A and this is the initial concentration of A. So basically this is concentration of A at any time t. The K is the rate constant, t is time, and this is the initial concentration. So to drive the law, basically assuming we have or consider reaction A going to give us a product, so the rate becomes R is equal to K concentration of A to the power 1. So when you integrate all of this, and we earlier on looked in our previous chapter or chapter 1 where we talked about calculus for basic calculus for chemistry students, we earlier on studied about the laws and the rules of integration and differentiation. So we looked at calculus earlier on. So I believe this session shouldn't be a headache that much. So after integrating this, then basically we are going to have the natural log of the concentration of A at any time t divided by the initial concentration of this is equal to negative kt. So when we rearrange this equation, then we come up with the concentration of A at any time t is equal to the concentration of A, then the anti-log of the natural log, which will give us e to the power negative kt. So take note of this formula very carefully because we'll be using it most often in our calculations. So this is basically the reaction or the equation. However, you can choose to take it's from this equation that we had this. So this is basically one way we can represent the equation. This one way we can represent the equation, or we can also represent it as this. So which one you are familiar with, just note that you can keep that in mind, as well as this. So this is also a simple way to remember the equation for first order reaction. So let's look at the half-life of a first order reaction. So the time taken for half the concentration of the original substance to drop to half its original value is what we call the half-life of a substance or a reaction. So for a first order reaction, the half-life is given as 0.693 over 2, K over K, which is the rate constant. So this is the first or the half-life of a first order reaction, 0.693 over K. So when we are given the half-life, we can calculate the rate constant, and when we are given the rate constant, we can calculate the half-life. Now, for plotting graph, we are having two ways, or we have two ways of plotting the graph in first order, where the exponential graph and that of the linear graph. So when you look at A, this is the exponential graph. So we are plotting the concentration of A at any time t against time. However, in the integrated, in the linear graph, we are plotting the natural log of concentration of A at any time t versus time. And usually the slope of the equation, the slope of the graph will give us negative k. This is because the slope of this will give us a negative value. So equating it to k will will cancel out to give our positive value for k. So usually we take y2 minus y1 over x2 minus x1, and that is how you calculate the slope of the reaction, and this will always give us a negative slope. Now, the time required for the reactant to reach half its original concentration, like I said, this is the half-life of a first order reaction, And remember, the half-life of a first order reaction does not depend on the initial concentration of the reactant. It does not depend on the initial concentration of the reactant. Now, let's look at the integrated law for zero order. So basically, the integrated law for zero order is the concentration of the A at any time t going to is equal to negative kT plus the initial concentration. Now, considering the reaction, there's when we find the integrated rate law, you should be arriving at what we earlier on demonstrated. And the half-life of the zero order reaction is represented as concentration of A divided by 2 times the rate constant. So a plot of concentration of A at any time t versus t for a zero order reaction, the slope is equal to negative k. So remember that these are always confusing most often, because when students look at this graph, they think it's a first order. Remember, in first order, we are plotting the natural log of A at any time t against time, not the concentration of A at any time t. So take note, in first order, we are plotting the natural log of the concentration of A at any time t against time. However, in zero order, we are plotting the concentration of A at any time t against time. So take note. Now, for second order reaction, this is the integrated rate law. So we have 1 over the final concentration of A equal to kT plus 1 over initial concentration of A. So if you integrate the rate law, then we should be arriving at this particular equation. And then the half-life is always the initial concentration of A divided by 2. So you realize that in the zero and second order reaction, the half-life depends on the initial concentration of the reactant. But in first order, the half-life does not depend on the initial concentration of the reactant. So for half-life of second order, the half-life of a second order reaction is given by 1 over K multiplied by the initial concentration. 1 over K multiplied by the initial concentration. So when you plot a graph for a second order reaction, usually we are going to get a positive linear graph, and the slope is always equal to K. This is because our slope for this graph is going to give us a positive value. We're going to give us a positive value. Okay. So, like we said, the half-life of a second order reaction is given by the equation half-life is equal to 1 over the rate constant times the initial concentration of A. Now, the half-life gets longer as the reaction progresses and the concentration of reactant also decreases. So, each successive half-life is double the preceding one. So, as a session review, how can you tell the difference among zero, first, and second order rate laws from their graphs? So, thank you, and I hope to see you in our next session.